In this presentation, I'll be explaining wind energy conversion systems. In that one, what is meant by fixed and variable speed wind turbines. Now let us see the wind energy conversion system, WECS. Its block diagram is shown here. That consists of at the front end, there is a turbine, that is wind is hitting on the turbine blades. Therefore, there's a turbine at the front end side, and uh, that is given, that rotation is given to the generator through a transmission gear mechanism, that is this transmission with the gear mechanism, and that's given to the generator, and the generator output is given to the grid, utility grid. In between there is a soft start. The soft start is to create electrical isolation between the wind turbine system and the grid for a very short time to limit the starting high inrush current of the induction generator during the transient period. That is the purpose of using soft start between the generator and the utility grid. And of course, to control all this one, there is a indicated as a microprocessor system that controls that senses different, like the wind speed and the voltage, current, etc. that controls this the turbine, etc. So this is a block diagram of a wind energy conversion system, and in that one, that is the this is as a schematic diagram of the wind turbine as such, and that is shown. There is the blade, and I mean, as a hub is the component that usually holds the blades and connects them to the main shaft of the wind machine. That is, the hub is the then main shaft that goes to the gearbox is the, of course, the braking mechanism is the, generator is the, and this is the tower on which this is kept as. Therefore, this is the housing system, housing of all this one, that is marked as housing. And therefore, this is a schematic diagram of a windmill system, and this is the block diagram of a wind energy conversion system. Continuing the parts of the wind turbine in detail. Therefore, this is the different parts of the windmill system as such. Here, rotor is there. Of course, the wind is falling on the blade, rotor, and the low speed shaft is there. And the low speed shaft, through a gearing mechanism, the speed is increased here, and that is given coupled to the generator, and the generator output is available. And there is a controller for that one. This is an anemometer for sensing the speed. The wind is there, and therefore high speed shaft is, that is the generator shaft is there, and the yaw motor that controls the yaw drive. It's also a yaw drive, and the yaw drive is used to keep the rotor facing into the wind as the wind direction changes. And this is only applies for the wind turbines with a horizontal axis rotor. So that is the yaw drive controller is the, braking mechanism is the. Therefore, this is the different parts of a wind turbine. Now, continuing the wind turbine different parts, that is the wind turbine is shown. This one diagram is shown here. The different parts are marked as, that's one much numbered here, and that is explained one by one. First one is the foundation. The foundation, it is that is this one foundation. It is the basement of the wind turbine on which the whole self weight of the wind turbines will come, and is normally under the surface and it cannot be seen. That is here below that one, that comes the foundation. And second, to the electric grid. Therefore, that is here, this is generator output is connected to the electric grid, and this is the connection from which the generated power is sent to the electric grid with the help of the electric wires. Therefore, that is marked as electric to the electric grid. Third one is a tower. That is, it is the supporting structure for nozzle and rotor, and the nozzle is placed above the tower. Tower is the assembly of the number of cylindrical hollow structure which are assembled at the side for wind farm. This is the tower. That is the third one. And the fourth is access ladder. That is, there will be a ladder inside the tower from the basement. That is this one, fourth one. There will be a ladder inside the tower from the basement to keep to the top, so that one can get access to the nozzle for any kind of repair or inspection work. For continuing the next slide are the different parts. For the four parts it is shown here: foundation to the electric grid, tower, and access ladder. Now continuing the wind turbine parts, yoke control. Yoke control, that is the fifth one, that is the yoke control. Since the direction of the wind keeps on changing with respect to the time, and the rotor should be placed in the direction of the wind to get maximum power output, this yoke controller helps in changing the direction of the rotor and will place it in the direction of the wind. That is done by the yoke controller, that is marked as 5. Number 6, therefore number 6, that is marked as, that's called nozzle. It is a rectangular like structure that contains generator, controller system, cooler, etc. When yoke controls activates, the whole nozzle is rotated in the direction of the wind. That is the number 6 nozzle. 7 is a generator. The number 7 is a generator. It is the unit responsible for the power generation. And 8 is the anemometer, that is here 8 is anemometer. It is a device that is used for wind speed measurement, and this data is sent to the control system. Therefore, these are the yoke controller, nozzle, generator, anemometer. We'll be continuing the next slide. Number 9, that is the brake. That is, this one is brake, and it is used to stop the rotor that is rotating. Usually brakes are applied when weather conditions are not good to generate the power, or the RPM of the rotor is above the normal speed, which may not be suited to generate. In that case, a braking mechanism is there, that is shown here. This is the brake system. Number 10 is a gearbox. The number 10, it consists of gears that increases the RPM of the rotor to suit to the RPM of the generator. That is number 10, gearbox. Number 11 is the rotor blade. That is here, rotor blade. Blades are the rotating member of the wind turbine that makes the shaft to rotate, which is connected to the gearbox and then to generate. Blades are of aerofoil shape, and the length will vary from 30 meter to 80 meter approximately, depending upon the rate of power generation of the wind turbine, rated power of the wind turbine. Number 12 is the pitch control. That is, this is the pitch control, and it's used to change the angle of inclination, pitch angle, which are responsible for getting maximum efficiency. The pitch angle, this angle is changed or blade to extract the maximum power, or that's called for getting maximum efficiency. That is, pitch control is there. 13 is the rotor hub. That is, here it is the one which holds the rotor blades, and it will also rotate along with the blades. For that is rotor hub. For brake, gearbox, rotor blade, pitch control, and rotor hub. For these are the different parts of the wind turbine. Now let us see the classification. Fixed and variable speed wind turbines. Wind turbines can be classified as fixed speed wind turbine and variable speed wind turbine. Therefore, the power derived from a wind turbine, that is in watts already we have seen, power equal to 0.5 Cp into rho into pi r square Vq, where Cp is the coefficient of power, rho is the air density in kilogram per meter cube, r is the blade length in meters, and v is the wind speed in meter per second. For this is the equation for the power derived from the wind, derived from a wind turbine. This is that is proportional to the cube of the, of course, the wind speed. So the power contained in the wind at a particular site is proportional to the cube of the wind speed. P is proportional to the V cube. Therefore, ideally, the maximum power that turbine can extract, as per ideally, it is the Betz coefficient, that is on the power, it is equal to 0.593. 0.593 of this much coefficient times the power contained in the wind. Therefore, this is the power contained in the wind. That maximum power it can be extracted, theoretical value, it is equal to, that's called Betz coefficient, it is equal to 0.593 times of this one. However, the maximum extractable power from the practical turbine limit is out of this one, it can extract practically. This is the ideal case of 0.593 of times this one. But in practically, maximum power that can be extracted is around 35 to 40% of the wind power can be extracted. Therefore, for a given turbine, this limit is achievable for a specific tip speed ratio, that is ratio of the turbine rotational speed to the wind speed, TSR, a certain value that can be obtained. For at another ratio, the turbine output reduces. For a specific value of tip speed ratio only, you can extract the power, maximum power from the wind that can be used to generate the electric power. Now coming to the fixed speed wind turbine. Fixed speed wind turbine is the schematic diagram is shown here. It's a blade of wind turbine. Through a gearbox, it is connected to the rotor of the generator, induction generator rotor. And this is the stator. Stator output is connected to the grid through a soft starter. As I already told you, soft starter is to create an electrical isolation between the wind turbine system and the grid for a very short time to limit the starting high current, inrush current of the induction generator during the transient period. To limit that one, we are using a soft starter mechanism that is between the stator of the induction generator and the grid. And here, of course, the reactive power compensation is required because this requires the reactive power. Power factor will be lagging power factor, therefore it demands the reactive power that's done by a compensator like a capacitor. Reactive power compensator is the, therefore this is the schematic diagram of a fixed speed wind turbine. And in fixed speed wind turbine speed is fixed independent of the wind speed. Whatever be the wind speed, the speed is fixed in fixed speed wind turbine. And the rotor speed of the wind turbine is fixed by gear ratio, supply frequency, and generator design. And fixed speed wind turbines are coupled with a induction generator. That is, fixed speed wind turbines are coupled with an induction generators which is connected to the grid directly through a soft starter and a capacitor bank. This is a capacitor bank. Through that one, this induction generator is coupled to the grid. And design of such type of wind turbine is done to achieve maximum efficiency at any one particular speed of the wind. Any particular one speed of the wind, it is getting a maximum efficiency in such a way it is designed. Therefore, that is in fixed speed turbine, with the turbine speed is fixed independent of the wind speed. Therefore, that is a fixed speed wind turbine. Therefore, this is a schematic diagram here of the fixed speed wind turbine. Now, continuing the fixed speed wind turbine. Fixed speed wind turbines power protection can be increased by using two winding set of generator. In induction generator, two sets of winding can be used. One for the lower number of poles, another for the high number of poles. So for typically, just an example, one set is for a low wind speed, will be using more number of poles, and high speed will be using less number of poles. Therefore, one set is used for a low speed case, will be number of poles is more here. Another set of winding that is used for high speed application or medium speed application, here typically number of poles is less. As an example here, for an 8 poles case at the low speed application, and 4 poles are used for a medium or high speed application. There are two sets of windings are using in this type of fixed speed wind turbine application. Since the turbine operates at a fixed speed, fluctuation in the wind speed is transmitted as a fluctuation in the mechanical torque. Therefore, because since the turbine is operating in a fixed speed, as you know that one torque into, of course, as the wind speed is increasing or as that changes, as the input power, mechanical power is changing. Therefore, as wind speed is constant here, as you know that T into omega is the power. Therefore, as the power is changing, since if you are keeping the speed is constant, omega is constant, then T has to change. Therefore, as we are keeping the wind speed constant, the fluctuation in wind speed that will be reflected as the fluctuation in mechanical torque produced. Therefore, the speed is transmitted as a fluctuation in mechanical torque, and therefore the fluctuation in electrical power into the grid, that will be reflecting as a fluctuation in electrical power to the grid. Because of the fluctuation in torque, there will be a fluctuation in electrical power in the grid as the the wind speed changes, because the turbine is operating at a fixed speed. As since it is running at a fixed speed, as the mechanical input, or what we call the wind speed or wind power, is increasing, torque changes. T into omega is constant, or T into omega is input power. As input power is changing, as omega is keeping constant, torque has to change. That is why the mechanical torque changes, that will be reflected as the fluctuation in electrical power into the grid in a fixed speed wind turbine. For a weak grid, this power fluctuation creates a large voltage variation in the and significant line loss will be producing for a fixed wind speed case. And this is the wind speed versus power extracted for fixed speed wind turbine system, in which here can say that one there are the active stall, that is active stall here. After this one, whatever be the wind speed, we can say the power output is made constant. And here also this is called the passive stall. The purpose is that if the wind speed is above that limit, then the power output is kept made constant by this mechanism, like of course pitch control, active stall control, and passive control. The output power of this wind turbine is kept constant if the wind speed is above a certain value. Now continuing the fixed speed wind turbine. In fixed speed wind turbines, power is limited aerodynamically by means of either the stall control, that's what I'm telling, that is limited by either by the active stall control or active stall control or pitch control. The power is limited by that one if the spin speed is above a fixed, certain limit. So the soft start is used for reduction of the inrush current and thereby to limit the flicker problem on the grid. And reactive compensator is required in such turbines to reduce, almost to eliminate the reactive power consumption from the turbine generator. We have to add capacitor bank to compensate the reactive power requirement. Therefore, this is achieved by continuously switching the capacitor bank that is connected. Now continuing the fixed speed wind turbine. Advantages of fixed speed wind turbine is already shown this schematic diagram. Design of fixed speed wind turbine is simple and robust. This type of wind turbine is more reliable. Cost of power electronics elements used in this turbine is less. And these are the advantages of this type of fixed speed wind turbine as such. And reactive power compensation is more here. The reactive power is to be compensated. Whatever the reactive power required for the generator is to be supplied by capacitor bank. For reactive power compensation is more, that is a disadvantage. It creates more mechanical stress on the turbine because as the wind speed changes, the torque changes. And due to the fixed speed operation, large voltage variations are produced to the it's actually wind speed fluctuation. Large voltage variation will be producing. That is the another disadvantage of this one. Therefore, due to the fixed speed operation, large voltage fluctuations are produced to the wind speed fluctuation. As wind speed changes, there will be torque fluctuations that will be causing the power injected into the grid, and that will be causing the voltage fluctuation. That is another disadvantage of fixed speed wind turbine. Now let us see variable speed wind turbines. Second one. In that one, with a change in wind speed, which is in a natural occurrence, it is desirable for the turbine speed to be adjustable to the wind speed in order to maximize the output. That is implemented, that is available in the case of variable speed wind turbines. For this, it is required to have a variable speed operation of the wind turbines along with the suitable power electronic, that is electrical power generation system or sustainable generator. This variable turbine speed operation is possible with a pitch angle control. Besides increased output, variable speed turbines operation has many other advantages in contrast to the constant speed operation of the generator in conventional power generating stations. But this operation requires additional power electronics devices to convert the variable voltage and variable frequency of output that comes from the electrical generator, which can not be directly connected to the grid. Therefore, there is a power electronic converters are required to convert first variable voltage, variable frequency into a DC quantity. Then again, that is to be inverted. Using the power electronics inverter circuits to the required frequency of the grid. Therefore, that power electronic circuits requirement or that operation of the requires additional power electronics devices that is required in a variable speed wind turbine system. Continuing the variable speed wind turbine system, a design of variable speed wind turbine is done to attain maximum aerodynamic efficiency for the wind ranges of the wind speed. And that is shown here, schematic diagram is shown here. This is the blade, and there's a, aerodynamic, asynchronous or synchronous generator as such, and that is given, output is given to a AC-DC converter, again a DC-AC converter that is connected to the grid. For due to the variable speed operation, rotational speed of the wind turbine, that is omega, can be adapted to the wind speed V. It means that variation in wind speed can be adopted by rotor of the wind turbine, or rotational speed of the wind turbine is accelerated or decelerated as the speed of the wind. And tip speed ratio lambda is kept constant at a predefined value which corresponds to the maximum power efficiency. Continuing the variable speed wind turbine. In contrast to fixed speed wind turbine, variable speed wind turbines maintains the generator torque fairly constant. Unlike fixed speed, here the torque is fairly constant, and the fluctuation in the wind speed are absorbed by the variation in the speed of the generator. Therefore, the torque is relatively constant, or that will be fairly, it is constant in this case, variable speed wind turbine. As compared to the fixed speed wind turbines, variable speed wind turbines are complicated electrical system. That involves the converters. Two converters are first yet to be converted into DC, AC to DC, variable voltage, variable frequency into fixed DC. Then again it is to be converted into AC, or it is DC to AC, that is connected to the grid. Therefore, there are that involves, as compared to the fixed speed wind turbine, variable speed wind turbines have complicated electrical system. In variable speed system, generators are not directly connected to the grid, but connected through a power converters. Advantage of power converters connected to the grid is active and reactive control is fast in this case, unlike fixed speed wind turbine. Continuing the variable speed wind turbines, generator speed is controlled by power converters, and power fluctuation created due to the wind variations are absorbed by means of changes in the rotor generator speed, and consequently the wind turbine rotor speed, and the rotor speed is changing proportionally. Therefore, here basically in a variable speed turbine, variable wind turbine system, there will be power converters are using. One converts AC to DC. For the variable voltage, variable frequency that is available at the stator of this one, and asynchronous generator, that is that DC is again converted into AC, that it can be connected to the grid. Therefore, there's a converter at the front end side, this side, as well as at the grid side. There are two converters are required. Same schematic is shown here also, and that is here there are different types of sensors as well as torque controller, or this is a variable speed wind turbine system as a schematic diagram. And of course, the generator speed is controlled by the power converters in this one. The control of these power converters will do the generator speed control as such. Therefore, this is a variable speed wind turbines in which depending upon the wind speed, the speed of the generator changes. Continuing variable speed wind turbines, what are the advantages of variable speed wind turbines? Mechanical stress on the wind turbines are less because it is running at the variable speed, and therefore the torque change is less. Therefore, the mechanical stress is less. They can attain maximum aerodynamic efficiency for a wide range of wind speed. Energy capture rate is high in these turbines compared to the fixed speed wind turbines. Disadvantages are structure of electronics element is complicated. Because of the additional power electronic converter system and control cost is more here, and loss in power electronic switches. Therefore, these are few disadvantages, but there are advantages for the variable speed wind turbines. And again, the same schematic diagram for a shown for a variable speed wind turbine. There are two converters. In this case, two converters and its control circuit is required. So that is because of the additional power electronic system and control, cost is more. Now continuing the comparison of fixed and variable speed wind turbines, and of course power quality issues, and fixed speed wind turbine with a direct connection, and there's a variable speed wind turbines with indirect connection, like a power converters are used here. First one, reactive power. In this one, fixed speed, there's no power electronic circuit, but we have to connect a capacitor bank. Separately, we have to connect a capacitor bank in this case. Therefore, there's no control of the reactive power as such here. You require a separate capacitor bank here. But in this case, the control of reactive power can be done by controlling the converters. The reactive power can be injected, that can be controlled as such by using these converters. But that's not possible in this case. We have to connect capacitor bank separately. Therefore, that's regarding the reactive power requirement. Second one is the harmonics. Do not generate harmonics, but here harmonics are generated by the converters. There are harmonics will be more in this case. Variable speed wind turbine with the indirect connection, so that is like this one. Voltage dips because of the high inrush current, the direct starting mode that may cause voltage dip in this case. But here control of voltage level is possible in this case. And the fourth one is voltage variation and flicker. Due to variation in the wind, as we have seen, there will be changing torque that causes variation in the power injection, that will be causing the variation in the voltage. In this case, fixed speed case. For that, due to variation in the wind, there will be voltage variation and flicker, but that is less in this case. Improved voltage stability can be attained in a variable speed wind turbine. The transients caused by the short or shunt capacitors during the start and stop, caused by that, because capacitor banks will be connected. Due to that one, transients will be caused by shunt capacitors during start and stop, but limited transient level is there in the case of variable speed wind turbines. And frequency variation in autonomous grid, due to the sudden wind drops or rise, there will be frequency variation, but improved frequency balance. Therefore, there's no much frequency variation in this case, a variable speed wind turbine system. So these are the comparison of the fixed and variable speed wind turbine systems.